Jonica, and thank you to the organizers for having us all here. So let me just jump right into it. As we've heard throughout the course of this conference, the next frontier for learning about dark matter is detecting halos that don't have stars in them. Sometimes these are called the Holy Grail, right? Detecting these things. And detecting them would be remarkable from kind of a human standpoint and also very useful for constraining dark matter models. And Simona has just gave a very interesting talk about a type of lens system where the observable is the surface brightness of an arc. The types of lenses that I will be referring to and discussing in my talk is it's a different kind where you have a multiply imaged quasar. So just to be clear about what we're talking about here, these are 4 examples. The thing in the middle is a galaxy. Apparently I need to do a software update. Oh no, all right, good. The thing in the middle is a galaxy. The 4 bright spots around the galaxy are 4 images of a quasar. And then some of these also have lens darks, which if I talk quickly, maybe I will get to how we can model lens darks as well as flux ratios. And as I just said, the flux ratios or the relative brightness among these images is the observable that I will be focusing on. And the reason is because these are, if you imagine you have all the mass in one lens plane, the magnification of an image is proportional to second derivatives of the potential. So these are very localized probes of the local mass density near an image. And what I'm showing here is the magnification cross-section of a 10 to the 7 solar mass halo. If you imagine you have a lensed image appearing right in the middle of this panel. The percent that the presence of this halo changes the brightness of an image depends on the source size. In this case, the source is extended by around 80 parsecs. This is what we can get with current existing data with the Hubble Space Telescope. And the reason why we select these kinds of extended sources is because the flux ratios of these lenses will not be microlensed. So they will be millilensed by these low mass dark matter halos, but not microlensed. As you get down to 10 to the 6, for this kind of source, it's too extended and we don't really detect these objects. However, this will now change. There's a JWST program led by Anna Nierenberg, and it will collect measurements of the flux ratios in 31 lens quasars in the mid-infrared. So this emission is around 10 times more compact than the emission that we can detect with HST. And then you can see that a 10 to the 6 solar mass halo becomes, imparts a 5 to 10% change in the brightness of an image. Okay, so this is all very exciting, right, but there's many steps going from this kind of statement about what you can detect with flux ratios and then actually making statements about dark matter. And as Simona was saying, lens modeling is quite complicated. In general, there are many different ways to configure a galaxy and put substructures in front of it in order to reproduce a given data set. So if we actually want to extract information from lenses, we need a way to statistically constrain dark matter models and tell the difference between something like a multipole perturbation or a population of halos. So in the next couple slides, I will try to give a crash course on how this works. There goes the mic. So on kind of a very high level, this is what we do. We start with some dark matter theory that we're interested in testing. It will make some predictions for the form of the halo mass function and the density profiles of halos. We will simulate lenses millions of times for this dark matter model, and we will make essentially fake lenses that look like the real thing, and then we'll make some kind of statistical comparison between the simulated data sets and the real data set to draw conclusions. So a lot of the work goes into to making realistic or forward modeling realistic lenses. And so of course, when we do this, we have to have accurate prescriptions for the phenomenological aspects of the dark matter model that we're testing. So is the halo mass function a power law? Does it turn over at some scale, for example? And then, of course, there's also several other kind of nuisance parameters that we have to deal with that we also include in the lens model. These are things like satellite galaxies, deviations from ellipticity, angular structure in the lens, the finite size of the background source, and then, of course, your statistical measurement uncertainties. And I just want to be clear, there are actually many codes to do lensing. in addition to Pi Auto Lens. So Lenstronomy is another open source lensing software that you can use and pull off GitHub. And then I've also written some open source code that you can use to do this kind of science if you would like. So I'd like to describe the methodology in the context of warm dark matter because I think there's some physical intuition for how warm dark matter behaves and what kinds of substructure populations we might expect. So in CDM, right, you expect essentially a scale-free halo mass function all the way down to something like the mass of a planet. In warm dark matter, you have fewer halos, and you might expect that in cold dark matter, we would expect more frequent and stronger perturbations to the brightness of images because halos are more numerous and they're also more concentrated. Right? Keep that in mind. So once we're able to generate plausible configurations of dark matter halos, we start lensing them. So we shine quasars through them. We propose lens models for the main deflector. We perform these simulations 1 million times or hundreds of thousands of times for each lens. And what we then do is compute observables. So I will kind of focus on the flux ratios, as I've said. So this is actually, this is the output of these simulations, what you might get. In CDM, you have this distribution of one flux ratio. Of course, there are 3 flux ratios. I'm just showing one because it's a little bit easier to interpret. So you might have, more perturbation in CDM than in warm dark matter, which sort of intuitively makes sense based on the number of halos predicted to exist in these models. And then you suppose that you've actually measured this flux ratio for a given lens, and you measure this value. And from this, you can now use your simulation to define a likelihood function. And once you have a likelihood, you can then derive your Bayesian posteriors and confidence intervals. Okay, so this is kind of your frequentist's spin on Bayesian statistics. It comes with many different names, right? Simulation-based inference, approximate Bayesian computing, things like this. And then I just want to stress before I go on that all of these simulations, all of the things I'm talking about are tested and validated on simulated data. So before we actually apply this to real data, we make mock data that includes the systematics that we know about, so the things I discussed on a previous slide. And then we analyze that mock data as we would analyze real data and verify that we get the correct answer, or that we are not systematically biased by some unacceptable amount. I don't expect you to interpret this collage of corner plots, but this is just to show that we test this machinery on simulated data. So the first application of this method to real data was done in 2020. We used a sample of flux ratios from a series of Anna Nirenberg's papers that collected, that measured flux ratios from the nuclear narrowline region. So this was done with 8 lenses, and this led to a constraint on the free streaming length of dark matter and then the overall number of subhalos. These things are correlated because you can, to some degree, compensate for a turnover in the halo mass function by adding more substructures. So these are now out of date. A few weeks ago, there was the first series of papers presenting constraints from Anna's JWST program. These improved the constraints that we obtained several years ago. This was work led by Ryan Keeley, who's somewhere in the audience. And if you would like to know more about this work, you talk to Ryan, okay? And let me just stress that this is just the beginning. This was done with 9 of the 31 lenses, and so around 2/3 of the sample hasn't yet been analyzed. Okay, so that's all I'm going to say about warm dark matter for this talk. I'd like to kind of look forward to other kinds of questions we can ask with these data. And the first class of theory that I'm going to talk about is self-interacting dark matter. And as you can guess, here the process of core collapse is the phenomena that allows us to test these theories with lensing. And then, with the interest of being kind of very forward-looking, what is the most ambitious type of question we can ask with lensing? I want to talk about some of this work where you can use the properties of dark matter halos to, you can interpret inferences of the properties of dark matter halos in terms of the initial primordial power spectrum. So this is now getting into the physics of inflation in the early universe. Okay, and then if I have time, I'll tell you about some fun lens modeling stuff that we can use to do better in all of these science cases, but I'm not sure if I'll actually get there. So we'll see. Okay, self-interacting dark matter. First of all, what do I mean by self-interacting dark matter? I'm just going to say that this is a form of dark matter that potentially has no interaction at all with the standard model, but it does have some interaction with itself. I'm going to demand that it preserves the large-scale structure of the universe and that it behaves collisionlessly at high speeds to evade constraints from things like colliding galaxy clusters. And the way that you satisfy in particular this third constraint is by demanding a velocity-dependent cross-section. Because if you have a velocity-dependent cross-section, you can suppress it, kind of to some arbitrary degree at very high speeds, but then have a very high amplitude cross-section on the low-mass scales probed by lensing and dwarf galaxies and potentially stellar streams. Now, if you have a repulsive potential, these cross-sections tend to look like power laws and velocity. If you have an attractive potential, you can actually get a much more interesting phenomenology. So as this video plays, I'm just going to increase the strength of this interaction and then show what happens to the cross-section as this number grows. So what you're seeing here is the evolution of different resonances in the cross-section. So this is a purely quantum mechanical effect that, as you can see on the y-axis, is changing the cross-section in low-mass halos by orders of magnitude. So these kinds of models exist, they're out there, and we could in principle think about testing them with lensing or dwarf galaxies or really any other probe that allows you to study the structure of these low-mass objects. And just to be clear about what this means for lensing, for concreteness, let's suppose that the cross-section is a power law and velocity to some power. We'll say alpha equals 2 here. In practice, this depends on the particle physics model. It could be shallower or steeper. So, but if this goes like 1 over v squared, if you have a cross-section that's ordered 10 centimeters squared per gram on the scale of dwarf galaxies, by the time you get down to 10 kilometers per second at 1 kilometer per second, this becomes 100 or 1,000 centimeters squared per gram. And this is the regime where basically the properties of these low mass halos that you can detect with lensing and other probes start to look very, very different than the properties of halos at larger masses. As I mentioned, core collapse is the phenomena, like it's kind of the ultimate fate of these halos, particularly if you have a very strong cross-section. And just to be clear about what I mean, right, if you start with the CDM halo profile here and you turn on self-interactions, you get first a core that kind of grows until it reaches some maximum size, and then eventually this process turns around and the core collapses. So these objects look like power laws in mass, like r to the minus 2.5, r to the minus 3 almost in some cases. And the connection with lensing is that a core collapsed object becomes a very efficient lens. So if we look at this kind of three-dimensional view of a lens system, and we start looking down the line of sight, here I've chosen a color scale that represents the density in dark matter halos. What you see here is in CDM, you get something that looks, sort of reasonable. If you allow core formation to happen in self-interacting dark matter, you remove the cusps of these halos, which is kind of the part of the phenomenology that has motivated interest in SIDM. And then if you allow some significant fraction of them to core collapse, then you can see by eye what happens to the critical curve here, which in this case is serving as a proxy for the magnification of images. I'm not going to go too much into how we actually model this and implement it in some kind of analysis. I'll just say that you can kind of understand core collapse as something that occurs over a characteristic time scale, and if you identify what this time scale is, you can predict how many core collapsed objects might exist in front of your lens, and then you can phrase the constraints as constraints on the core collapse timescales here. So for this particular class of cross-section, which is kind of a repulsive semi-classical type cross-section, you can derive constraints on these core collapse timescales, which I realize this is a very busy plot. But basically, with existing data, you can rule out this bottom corner parameter space, which is a situation in which essentially every dark matter halo in the universe has core collapsed. If you're interested in this, I'm happy to talk more about it, but for the sake of time, I don't want to go into too many details. I will just say that this will get much better with the JWST data because the source is so compact. So if we take a core collapse 10 to the 6 halo, it does produce some kind of detectable effect in the extended sources that you get with HST, but with JWST, it becomes very, very obvious And so if there's a large population of these core collapsed objects out there, we should be able to detect them. Okay, so I'm probably getting a little behind. So kind of thinking about what is the most kind of ambitious thing that you might want to do with these data, right? What is the kind of the, thanks. What kinds of questions can we ask that really push the limits of the amount of information we can extract? You know, so this is by now probably a familiar figure for many people. This is the linear matter power spectrum. And this linear matter power spectrum is the primordial matter power spectrum, which is predicted by your favorite inflationary model, times the linear theory transfer function. Okay? Now, when you change dark matter physics, you change the transfer function, but you are free to interpret changes to the power spectrum in terms of changes to either quantity. So for the next couple of slides, I'm going to focus on the situation where you suppose that you know cold dark matter is true, but maybe you don't know the initial conditions of the universe, and you want to change the primordial matter power spectrum. And the key point, okay, sorry, and then I should say here that for this kind of analysis, we chose just kind of a phenomenological description for what the power spectrum does only on small scales. So this looks kind of familiar to a running spectral index and then a running of a running, but it's different because it doesn't do this on large scales. It only does this on small scales. If you're interested in what the physical motivation for this is, there are some kinds of kind of non-standard inflationary scenarios or other phenomena that can manifest like this in the primordial power spectrum. And the key point here is that lensing allows you to measure not just the abundance of halos and their concentrations. And this simultaneous inference is actually what allows you to do this kind of measurement. So what I'm showing here is the halo mass function, the Sheff-Torment prediction, and then a fit. It's useful to have a parametric model to actually build into the lensing pipeline and get constraints. So this is the halo mass function for different running. I'm just going to call it the running of the spectral index for simplicity. And you can see here that as you add small scale power, you change both the amplitude and the slope of the halo mass function. And a similar thing happens here with the concentration mass relation. As you add power, you change both the normalization and the logarithmic slope of the concentration mass relation. And so if you want to constrain this with lensing, there's basically a few steps. So first you go out and you try to measure the halo mass function and the concentration mass relation. You get some likelihood, and then you interpret that likelihood in the context of a model that connects the properties of the power spectrum to the slope and amplitude of the halo mass function and the concentration mass relation. So that's what we tried to do. So this was done with 11 lenses. These parameters are essentially the number of halos, the slopes of the concentration mass relation, and the halo mass function. It looks like nothing is really constrained here, especially if you look at the marginal likelihoods. But what's cool for this kind of science is that it doesn't actually matter to get a strong marginal likelihood constraint on one of these parameters. And it's because of the way lensing constrains these models. Here, the point here is kind of the CDM prediction in this space. And as you might recall from my earlier slides, if you add small scale power, you make halos more numerous and more concentrated. So the model predicts something that cuts through the space like this. On the other hand, right, if you decrease small scale power, similar to how you might do it in warm dark matter, you make halos less concentrated and less abundant, and so you move this way. And this likelihood, which you get from lensing, is essentially telling you that for a fixed amount of perturbation in the data, halos must become less concentrated as they become more numerous. So here the constraints that you get from lensing are orthogonal to the consequences of changing the properties of the power spectrum on small scales, and it's this kind of convenient feature of the analysis that leads to constraints on the power spectrum. So again, starting from this kind of measurement, you can then interpret it in the context of models that predict the halo mass function and the concentration mass relation. You get constraints on these parameters that describe your the power spectrum, and then you can then turn this into, thank you, this kind of inference on the primordial power spectrum. So what should you believe? What should you take away from this? Well, you should keep in mind, right, that this is a model-dependent statement for the primordial power spectrum. I'm not claiming that for any power spectrum it's constrained to this degree. So it's a model-dependent statement. And then the other thing that is kind of unfortunate is we don't really know how structure formation works on these small scales with kind of deviant forms of the power spectrum. This is an unsolved problem. And it would be great if we understood how to do this, because it would allow us to do this kind of science much better. However, unless the foundations of what we know about, for example, pressure vector theory and the halo concentrations, unless it's totally wrong, we will always be able to constrain these models with lensing, because lensing measures the abundance of halos and their concentrations to be anti-correlated, whereas they will always be positively correlated if you change the power spectrum. So I just got a note from Annika that I'm out of time, so I'm not going to talk about the fancy new lens modeling stuff, but I will just say that if you use the lensed arcs in addition to the flux ratios, you get a more robust model prediction for what the flux ratio should be. This allows you to limit potential sources of systematics and then do better in your dark matter inferences or in your early universe inferences. So, okay, I'm going to finish, go through my remaining slides, and then leave the takeaways up here. Just remember that this is very early days for this kind of research. Right now the results I showed were done with order 10 lenses. We will soon have 30, and then in the next decade we'll have hundreds. And so you can look forward to much more exciting research. Thank you.